Good morning, everyone. Can you please confirm if you can hear me? All right. I can see that almost everyone can hear me. So that's amazing. So what we are going to do is yesterday we posted a few quiz questions on our social media platforms and many of you participated in it. So just as a token of appreciation to you guys, we are going to give a surprise gift. So in our yesterday's quiz, we have about 166 people that have participated in it. So we are randomly going to pick one person out of this 166 and then give away the prize. To do that, I am going to use Google's random number generator. And the way it would work is I give a range. So for example, if I say the range is 1 till whatever random number, and I click generate, it would randomly pick a number. So in our instance, the maximum number is 166. So I am going to put 166 here. So between numbers 1 and 166, we are going to pick one random number. And without any further delay, let's do this. 3, 2, and 1. The number is 77. So let's see who is the lucky person. So, Gopalakrishna JSV. Mr. Gopalakrishna JSV, congratulations. You are our lucky winner for today. Our team will get in touch with you and we will give you a surprise gift. And even today, after the session, we will post the quiz questions on our Facebook and LinkedIn. So if you would like to participate, you can just comment your answers there and then we will include you in tomorrow's giveaway. And many of you were asking where can we watch the replay videos, and for the replay videos we have posted a link in the sticky note, and I'm also posting that link in the chat. If you click on the link, it will take you to our YouTube channel, and just give it a few more seconds to load. Yes, and these are our YouTube videos. So today is day 16. That will be added to this playlist very shortly. And we have all the previous days recordings. So right from day 1 all the way till day 15. And if you have not yet subscribed to our channel, I would request you all to please subscribe. You would find a button right next to our logo here. So you can click on that subscribe button and you can subscribe. And let me just check. So
yeah, Enoch, I'm there.
All right, thank you, Barney. Over to you.
Thank you so much. Yeah. And who won the prize? Sorry.
It was Gopalakrishna JSV.
Hey, hi! Congratulations, Gopal Krishna, for participating and winning this prize. I truly appreciate your effort that you have put in. And everyone who is participating, yep, it's not about winning, but it is all about learning and being active on social media, right? Okay. So once again, here is the mind map. You would find a comprehensive mind map here. And please be active. I'm also, as I've told you, we are writing digital book for the time being, and we want to launch it on 15th August. And when we launch it on 15th August, we want to give away a free version of that to people who are there on the social media. Okay, not everyone. So that is also another incentive for you all to be on social media. And there we go. So we started off with crisp DM. We understood the business problem. We collected the data. We cleansed the data. And then we resorted to machine learning, supervised learning. And we are discussing about black box techniques within which we are discussing about neural network. And we are here at recurrent neural network. Post that we will proceed further with LSTM, then GRU, then mask RCNN, faster RCNN, speech recognition, and no chatbot. We will not get into that, but then we will again look into autoencoders, GANs, Boltzmann machine, and then reinforcement learning. This is how it is structured. But after your GRUs, the rest of the things would be more of theory and will be, because we need to at least have a brief understanding about all the various algorithms which exist. So we'll understand all the various network architectures which exist. Having said that, here we go. RNN. So when it comes to RNN, or when it comes to textual data, basically, you might want to use your traditional language models like text mining or NLP, or you might want to use MLP also, multi-layered perceptron. But the only challenge is it doesn't capture the sequence. Okay, and it also would not store the data in memory. For example, if someone says Andhra Pradesh and Telangana bifurcated a few years back, and then they explain about the brief history on what happened, how it happened, and all that. And suddenly, in the 10th paragraph, if they say these two states, then we should be able to understand, or your algorithm should be able to understand on what are those two states. Okay, so AP and Telangana, okay, bifurcated. Somewhere in the first paragraph, you have this. Then somewhere in the 10th paragraph, if they say these two states, what are those two states? How will your computer understand? Okay, so you need an architecture which can store the information in memory, store the previous information in memory. If it can store the previous information in memory, then we can proceed further. Otherwise, no. Yeah. So for that reason, people have done some research and came up with recurrent neural network. Okay. A few key things about RNN would be, I'll put it here, RNN uniqueness. One is it can store the historical words in memory. This is one greatest advantage. And the second thing is weights are same across all RNN units. What does this mean? Say you have a word and a hidden network. You have a hidden unit, you're taking that. There we go. Yep. So again, you take it forward in this way. And then you have an output. Each one of these is an RNN unit. This is another RNN unit. This is another RNN unit. RNN unit. You have multiple RNN units. The weights are same across all RNN units. That means the weights that you have here, here, and here will all be the same. The weights which you have here, here, and here will all be the same. Right? That is the meaning of weights are shared. And how are the weights updated? Weights are updated using back propagation through time. However, having said this, there is a disadvantage with back propagation through time. And what is the disadvantage that we have discussed yesterday? That if you have too many RNN units, if you have too many such units, and if all of these weights are initiated such that they are all less than 1, if they are all less than 1, null hidden layer, then you keep multiplying values which are less than 1 throughout. And if you have all the values which are less than 1, if you keep multiplying, the values become smaller and smaller and smaller, such that even before your algorithm reaches the minima, your algorithm would stop because gradient would vanish. Vanish means it becomes 0. So that is gradient vanishing gradient problem. And we also have another problem, which is exploding gradient problem. Exploding gradient problem. In the same example, if the weights which get initialized randomly, initially it is random, when the weights get initialized randomly, and if the weights are greater than 1, if you keep multiplying those values over a period of time, it explodes. It becomes so large that your algorithm might skip and go here. It might skip this local minima. So you're missing out an opportunity to be at the minimum surface. Okay. So even before that, we had language models. What were the disadvantages of language model? Disadvantage is that you need huge memory to process n-grams greater than. If you have more than 3 trigram, you need huge memory. This is one thing. Second, cannot store historical text in memory. These are the two disadvantages. And hence what we have done is we thought, okay, let's try out MLP on textual data. When you try out MLP on textual data, what happens? When you try out MLP on textual data, the number of weights will come down, but still the weights are significantly high. Weights or parameters to be learned are significantly high. One. Second is, again, cannot store historical data in memory. Historical words, basically. Hence, we resorted to RNN. Oh, sorry about that. Then we have this. Just give me 1 minute. Extremely sorry, friends. Just give me a minute. Here we are. Sorry about that. Yeah, a few things are unavoidable. So, yeah. All right. Next, we tried out language models. Then we tried out MLP. Then we resorted to RNN, okay, which works based on back propagation through time. And how do you solve it? Solution to the disadvantages is truncated back propagation through time. Okay, truncated BPTT. And here also the same thing, back propagation through time is used. I mean, back propagation technique is used to update the weights. And what is the loss function we use? Usually you use cross entropy, or there is something called as um, KL divergence function. Usually we use cross entropy or KL divergence. And we also need to be aware of the variance, the flexibility which is given by RNN. RNN variance in terms of flexibility. What are the various variants that we have? We have something called as one-to-one. Usually using one-to-one means you'll have one input and one output is not advisable. This is called as a vanilla network. Usually people do not prefer that vanilla neural network. Then you have one-to-many. Vanilla means plain flavor. Don't again think about chocolate ice cream and all that. Yeah, vanilla means a plain flavor. I mean, there is no variant in some sense. Yeah. Then you have one-to-many. Example of one-to-many could be image captioning. Image is a single input. Output could be many words because an image can have multiple words. Then you have many to one. Many to one, you have sentiment classification. That means you'll have many words and you're going to classify it as positive or negative. Then we have many to many. In many to many also you have variants, one is machine translation, meaning from one language to another. Okay, example could be from English to French. Okay, and then you have another variant of many to many wherein as and how each input goes out, you throw out output immediately. This is video classification at frame level. Each frame of a video would be given a name. Okay. Then we have the CNN RNN variant, which we have discussed, wherein supply images to the CNN, and here convolutional base, then assign the learned representations of CNN to RNN. Okay, this is how you do. But here, one more important thing is you have to define the start of sequence of image captioning and also mark the end. When do you say image captioning starts? When do you say it ends? This is something that we can look at. Then we start to look at bidirectional RNN. Okay, in bidirectional RNN, we maintain two hidden layers at a time. This is an important thing. You learn the sequences from left to right and from right to left. Learn sequences of text in both the directions, from left to right and right to left. And then we also have deep bidirectional RNN. Okay. Each intermediate neuron, it receives, okay, let me put it here so that it's easy. Each intermediate neuron that you have will receive one set of parameters from the previous time step and two sets of parameters from the previous RNN hidden layer. Okay, that's very, very important. Here also in both the directions, right? So I'll put it here. One input comes from left to right RNN and another input comes from right to left RNN. Let me rectify the here be left to right RNN. Okay, and yeah, this is what we have discussed, and I think this marked the end. And let me delete this part which is not needed. So you have text mining, NLP, all of these. And today we are supposed to run the algorithm, right? But before we run the algorithm, once again, we discussed about a few more things in terms of word embeddings, right? What does that mean? Firstly, we discussed about applications of RNN. Within applications of RNN, we discussed about document classification. Then, for example, identifying author. Identifying author of a book. Then we discussed about time series comparisons. It can be used for time series comparisons, meaning comparing two stocks. So example could be comparing two stocks. Third thing is, of course, sequence to sequence learning. Sequence to sequence means converting from one language to another. English, German. Then we can also do sentiment analysis. Simple. Go to Twitter, take all the tweets and tweets classification into positive or negative. Time series forecasting. These are the various things that you can do. Okay. And then we discussed that deep learning doesn't accept raw text. So I'll put here DL does not take raw text input. So what should you do then? We need to convert or transform the text into numeric tensor. Right? We already discussed about tensors. This process of transforming the text into numeric tensor is called as vectorizing. Okay, I'll get all these things updated, friends. No worries. So this should serve as even for 1 year, 2 years of BTech in AI. For entire 1-2 years, you can teach these concepts. Trust me on that. Right. So it will serve as a very good reference for their exam students, exam preparation, interview preparation, for reference to the professors and lecturers also. Then here we can do this vectorizing in multiple ways. Primarily, we'll talk about three ways. Three prime ways of handling this. First way of handling it is you segment the text into words. And then do what? And then transform each word into a vector, a vectorization, converting it into vector. Second thing is segment text into characters, and then you transform each character into a vector. Again, you can also extract engrams of words, characters. Okay, and then what do? You once again transform each engram into a vector. Collectively, all these units, okay, so words, characters, engrams that you split your data into are called as tokens, and this process to get tokens is called as tokenization. Okay, and there are two major ways of associating a vector with a token. Associating a vector with a token, there are two methods. What are those? One is called as one-hot encoding, another is called as token embedding. Why is it called as token embedding? Because sometimes your tokens could be words, sometimes your tokens could be characters, sometimes your tokens could be engrams. Okay, so Majorly we deal with words. Hence you can hence we can call it as word embedding. Majorly we deal with word tokens, and hence we call it as word embedding. Okay, so we have actually looked at this as part of our multi-layered perceptron. If you remember, okay, in multi-layered perceptron, when we dealt with IMDb dataset and Reuters dataset, we actually touched upon this. And then I told in RNN, when we discuss, we will discuss in further detail, right? Is what we thought. So let me go to RNN and we'll understand it in a better manner. Okay. So let's take this and then we'll proceed further. Where is the spider? Yeah, here it is. There are quite a few lines of code that we have to look at. So of course, we will not do, you know, uh, micro level line by line explanation now because we already have done it enough times. But anyways, the code would be provided to you. It will also be uploaded on learning management system. So you'll reap the benefits. Okay. Or you can watch the recorded video and type it. But trust me, if you do not type it, you will not learn. Okay. So I'm importing numpy as np. We are taking a sample. One entry per sample. In this example, a sample here is a sentence. One sentence is one sample. This sentence is another sample. So you take that. And you're building an index of all tokens in the dataset here. Then here you're splitting it. For word in sample.split, using split method, you are splitting it. In practical setting, you would get rid of all these kind of punctuation marks, this full stop, and if at all there is any the on the these kind of connectors, filler words, you get rid of those things in practical setting. And why are we putting length of token plus 1 here? Because 0 index number is not assigned to any of the words. We don't attribute index number 0 to anything. It is something like it is going to mark the beginning, the start of your sequence. Okay, and then by running this piece of code, you are storing the results. Okay, and you vectorize the samples. So let me run this and then show it to you. When you look at samples, here we have samples, right? Samples has the cat sat on the mat, the dog ate my homework, right? In that way. And then you do a token indexing. If you observe this, look at what happened. The is given a value, 8 is given a value, cat is given a number. In that way, you have all these token assignment which happened. And then what we are doing is we are doing a one hot encoding wherein you have all those words, right? 0 you don't assign it to anything basically, and wherever you find the relevant word you put a 1, in the other place you put a 0. What does that mean? you just take all these words, right? The is 1 and cat is 2. Then you have sat 3. These words, you're just putting it in the sequence. That's it. Nothing much. Okay. All right. This is word level one hot encoding. Now let's look at character level one hot encoding. Here you import string of data, and then here if you look at results, for each of the characters, there are 100 characters that you have taken. For each of those characters, you have one hot encoding which is performed. Okay, this is very trivial. You can just watch it and you'll just understand. But then this is important. Within Keras, there is an inbuilt Keras code. Man, we do not manually write that code that I've shown you because you resort to inbuilt way of dealing with it. So Keras has inbuilt utilities for performing one hot encoding of text at a word level or at a character level. And we import tokenizer. You're taking the sample. And then what are you doing here? You're saying that you want to create the tokenizer of the data, but you want only the top 1,000 commonly used words. You don't want all the words used in the document. You want only the top 1,000 words. Run it. Then you say tokenizer.fit on texts. So it builds the word index. Now here, when you say tokenizer.text to sequence, you're turning the strings into lists of integer indices. If you're not understanding it, don't worry, because you understand the logic. That is good enough. Because understanding the programming, it's not an overnight job wherein you just listen to this once and then you learn it. I believe a lot of y'all are from non-programming background. Yeah. So here we go. And by the way, we are also conducting a free Python training next month, but then we will notify only on our social media. So those are the benefits that you will not reap if you're not there on social media. So I leave it to you. If you want to attend the free Python training, then you should be there on social media. You should subscribe to our YouTube channel. Then you'll automatically be notified. You need not be worried. Okay. So what you do here is you are going to create one hot encoding in this line. By just running this code, tokenizer takes each and every token. If you look at sequences, tokenizer, right? So let me run this. I'll show you one hot results. So in this way, you do one hot results, one hot encoding. Okay, and then how can you recover the word index that was computed? You run this word index, and then the is given 1, cat is given 2, sat is given 3, so on and so forth. Homework is given 9. If you want to print only the unique tokens and see, there are 9 unique tokens which are found. Unique tokens. So if you observe this, you have the and the, but you have to consider the only once. Okay, 3 times in fact it's used, but it is counted only once. Then you have a variant of this one hot encoding, which is called as one hot hashing trick. This one hot hashing trick is used when the number of tokens is very large. Okay, so let me put it here. So you have one hot encoding, and if the number of unique tokens is too large, then we use one hot hashing trick. If the number of unique tokens are too large, then we use one hot hashing trick. What happens in this one hot hashing trick is, instead of explicitly assigning an index to each word and then keeping a reference of those indices, so what we are doing here is we are assigning an index number, right, to each and every word, and then we are also keeping a reference of these indices in dictionary, right? Instead of doing this, you can hash the words into vectors of fixed size. What does that mean? So you'll say that, but there are of course a few disadvantages associated with that. So if you have all the words, instead of, if you have 1,000 words, instead of having 1,000 different 0, 1, 2, 3, 4, in that way, instead of having 999, 0 until 999, instead of having those 1,000 indices, you'll say that no matter which word I have, I'm going to hash it, and I'm going to say that I'm going to represent each and every word in just 500 words. These I don't want. If any of the word falls in this, only then you'll consider that. Okay, so the advantage is that you can generate the token vectors as and how you need it. You need not already generate it and store it. But the drawback is that two different words can have the same hash. For example, if you have a word here which falls in 999th position, and you have a word here which falls in, say, 600th position, these two you're not considering, right? You're not considering these two because you're considering numbers only until 500. So this and this will appear all zeros. So these two terms, because you're hashing it at 500, will have all zeros. So any word which falls in this range of 501 to 999 would not be considered. That is a disadvantage. Okay, this is one small trick which people use when you have huge data. Now let us understand about word embedding, which is one of the most famous technique. It's a very powerful technique to associate a vector with a specific word. Here you have a single number associated. Here you have a single number associated with the word in that way. But you can also have series of words which can associate with a series of numbers which can associate with a word. Okay. Vectors which are obtained using a one hot encoding will be majorly sparse. What do you mean by sparse? Sparse means, if I were to open this, majorly you will find zeros. Okay, you have ones only in a few places. Majorly you have zeros, if you observe. So this is called as a sparse matrix. Sparse means majorly you will have zeros. And it is also very high in dimension. Because if you have 1,000 words, you'll have 1,000 columns. In this case, you'll have 1,000 different words. So vocabulary size would be very large. So let me write down the differences here between one-hot encoding and token encoding. So characteristics of one-hot encoding is that it has a sparse matrix, meaning majorly we will have zeros. Okay, it'll be high dimensional in nature and it is hard coded. This is one hot encoding. Then when it comes to token embedding or word embedding, the characteristics are as follows. Be dense. Dense means there'll not be too many zeros. Be having low dimensions, lower dimensional representation. And it is not hard coded, the numbers, they are learned from data. What do I mean by hard coded? Hard coded means, you just put in that way. Say you have cat, the first word. So you look at all the words in the English vocabulary, or maybe you take only the 1,000 words of vocabulary. Wherever you see a cat, you put a 1, rest all zeros. This is called as hard coding. But here, based on your data, your model will automatically learn on what number should be assigned to each and every word. Automatically it decides. Okay, so this is the prime difference. Now here, when it comes to word embeddings, there are two ways of obtaining. Two ways of obtaining the word embeddings. What are the two ways of obtaining word embeddings? One thing is word embeddings jointly with the main task you care about. So what you do here is you start with random word vectors, random numbers, and backpropagate to learn the weights. Okay, of neural network. Same neural network is what will run to learn the weights also. Second thing is, like we have seen the pre-trained model, we have seen pre-trained models in CNN. On similar lines, we'll see pre-computed, embeddings will be used. These pre-computed word embeddings are also called as pre-trained. Okay, so let us understand the logic first, even before we get into the programming aspects of it. So to help you all understand the logic, I'll write it down here. The simplest way to associate vectors or numbers with your words is to get started with a random set of numbers. Okay, when you get started with a random set of numbers, your algorithm will get started. It's like a random initialization of weights. You randomly initialize the weights in neural network. On similar lines here also, you randomly assign the numbers to your words. But the challenge with this approach is that whatever numbers are ultimately assigned to your words have no structure. Randomly you assign some numbers. It's good, but it's not the best because it will not have any structure. For example, if you have two words such as accurate and exact. So you have two words. One is accurate, another is exact. Accurate might have a different set of numbers to associate with this, and exact might have completely different set of numbers to associate with exact. But we know for a fact that accurate and exact can be interchangeably used. But your neural network, how does it learn? Your data, your networks are only as good as your input data that you provide, right? So to get a better structure from no structure, if you were to move to some kind of a structure, then what do we do? To get a better structure, let me help you understand by helping you understand about the geometric relationship between word vectors. Okay, so what I shall do is I'm going to help you understand by giving you the direction. So let me draw a plot here, 0, 1, 0, 1 in that way. And then say you have something called as wolf and tiger. These are the different words in your underlying data. You're taking that data and you want some kind of word embedding. Embedding means collection of numbers which can be associated with each and every word. So here, when you look at this relationship, there is some semantic relationship between the words. For instance, cat to tiger and dog to wolf. If you move in this direction, you're actually trying to move from pet animals to wild animals, right? If I say cat, it's a pet animal. Tiger is a wild animal. Dog is a pet animal. Wolf is a wild animal. So if you move along this axis, you are moving from pet animals towards wild animals. Similarly, there is another vector. If you go from dog to cat or from wolf to tiger, you are moving from canine to feline. Okay, in real world, when you perform these kind of word embeddings, there will be there will be many things based on which these kind of similarities are established. It could be related to gender. It could be related to plural vectors. Gender could be if someone says female, if some word says female, or some word says queen, you can associate. If someone says king versus someone says king, you know that it's singular to plural. So in this way, there are thousands and thousands of words which are interchangeably used, which both can capture the information about a gender, whether I say female or queen or air hostess, etc. So all these mean that we are talking about a gender called female, right? Kings, cars, buses. So these are all plural. Okay. Is there an ideal way to come up with a word embedding which also captures these kind of relationships? Is there any other way? Is the point that we need to discuss, right? But as of now, in the world that we live in, we do not have such a thing. Okay, so but people are working. Hot research area. These concepts are, and people are working on that. So from Keras, you can load this embedding and you can create an embedding layer. Embedding layer always takes two arguments. The first argument is what are the maximum number of tokens? Okay, maximum number of possible tokens. You have 1000, which is 1 plus maximum word index. Next, we have the dimensionality of the embeddings. You're giving us 64. This embedding layer, what it does is, you can think about this as a dictionary. Okay, what does this dictionary do? It is going to map integers or integer indices, integer numbers. These are all integer numbers, integer indices to a dense vector. Okay, you're going to map integer indices to dense vector. So what does this do? It takes integers as input. So you'll have this word index. Then you supply this to the embedding layer. Once you supply it to the embedding layer, what does this embedding layer do? It takes integers as input. It looks up those integers. It looks at those integers in the internal dictionary, and it returns the associated vector. So each of these will have a vector. Vector is collection of different numbers. So you can again think about this as 0, 1, right? So you'll have 1, 2, 3, 4, 5, 6, 7, 8, 9. So this is belongs to 9. So you put a 1 there and rest all zeros in that way. So it will take your word index, and then your embedding layer comes up with the corresponding word vector. This is what it does. Okay, remember always embedding layer takes as input a 2D tensor of integers, samples, and the sequence length. right? Where each entry is a sequence of integers. It can embed sequences of variable lengths also. Okay, you can just say I want 32, 10, 64, 15. You can give any numbers, doesn't matter. Okay, so yep, this is how it works. And this layer that you have, embedding layer, let me run it and show it to you on what happens if I run this. Let it come up here. No. So this embedding layer basically uh, returns a three-dimensional floating point tensor. This tensor, whatever you get here, whatever you get as an output here, okay, this can be used for further processing. You can give that as an input to your RNN model, or you can also give it to your one-dimensional convolution layer. And when you instantiate your embedding layer, initially the weights are randomly assigned, right? As with any other layer. These word vectors are gradually adjusted via your backpropagation. It does backpropagation and your weights are adjusted. So what I'm going to do now is, we have this TensorFlow Keras datasets, and we are going to work on this, and we are going to classify the movie reviews as positive or negative. We'll do that. Okay. So yep. So what we shall do is, I know this will be a little taxing for you all. So we will take a break for, you know, 10 minutes, and then we will come back. We will be back at 11:45 and we will take it further. I understand that it will be a little complicated, but bear with me. I'll do sufficient recaps and ensure that you understand every part of it. Yep. So just take a break and come back, friends. Welcome back. That's nice to hear. Can first start learning all these with interest. I felt that I know this basic awareness would have been great. Yep, Chandrasekhar, thank you for that. I wish to learn. Yep, you will learn. Yeah, definition is out of 100 elements. If more than 50 elements are zeros, it's called sparse. Kindly correct me. Yeah, yeah, you're right, Murthy. No, disadvantage with sparse matrix is a disadvantage certainly. Sparse could there is no defined thumb rule, Murthy, wherein we say greater than 50% zeros is sparse. There is no defined thumb rule as such. Sparse means zeros, empty. How many zeros? You could probably say it's 10% sparse, 20% sparse, 30% sparse in that way. Okay, all right. So let us proceed further and understand more about the exercise here. So to help you all understand this word embedding, we can also I can actually take a small example and solve it, but then let's proceed further. If at all you feel that it's becoming too complicated, we want a probably simpler example to deal with, we will certainly look into that. Okay, I have no problem in making your lives easier, but then let's understand. So one hot encoding, there is a limitation, right? And what is that limitation? When you do one hot encoding, there will be too many zeros. Sparsity will be more. Hence, we are proceeding further with embedding. Embedding layers will have a slightly condensed version of encoding. For example, if it is one hot encoding, you'll have list of all the words used in your vocabulary. Say you have taken IMDb reviews, movie reviews, okay, and you're working on IMDb movie reviews. In IMDb movie reviews, you have all the words, you have various words. One second, extreme, sorry, one second. Okay, sorry, friends. Okay, so you'll have all of these, and say in IMDb movie reviews, there are 1,000 unique words or 10,000 unique words. In all the reviews, all the words of English vocabulary might not be used. In the reviews that you are looking at, there might be 10,000 unique words. So here you'll have 10,000 such words, and you'll have all 0 0 0 0 0 everywhere. And say someone says um, best movie of all time. This word best, this word best would have one against the word best, right? You'll have movie, awesome, all those terms. Somewhere you'll have best. Say you have that best here. So against that, it will show one. Rest all will be zeros. For each and every word, say there is another word called movie. Again, you'll have that lengthy list, and everywhere you'll have zeros. Everywhere you'll have zeros. And At wherever you see this word movie, you'll have a 1, right? So you'll have those 1,000 unique, if you have 1,000 unique words in your underlying data on which you're analyzing, you'll have, if you have 10,000 words, you'll have 10,000 columns. You'll put zeros everywhere and you'll put a 1 against the word, okay, whatever is the word. This is one hot encoding. This is called as sparse. How much sparse depends on the number of words, okay? But then there is no defined thumb rule saying that greater than 50% do you call it sparse? Not exactly. But then usually it'll be 90, 100, sorry, 90, 98% sparse in that way. Then you have word embedding. One hot is one thing, then you have word embedding. Word embedding for the word called best, you'll have a shorter vector size. Vector is collection of numbers. It'll be something like 1, 2, 3, 4, 6, 1, 2, 3, 2. This is a number associated with best. In that way, there'll be some vectors, vector of words, which will denote each and every term. Here, to generate such a vector, these are all weights. If you have a neural network in this way, okay, all these are weights, 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 right? All these are the weights that you have. So one way is to learn the weights along with your model itself. So when you run your recurrent neural network, alongside running your network, you add an additional layer called as embedding layer. Okay, and then you learn the weights alongside. Come back, update the weights. As part of this updation of the weights itself, your model is going to learn on what numbers should be assigned to the word vector. Initially, there'll be random numbers. Slowly and steadily, those numbers get improvised. Like you learn your weights in your typical neural network. Okay, then another way is you take a pre-trained model of word embeddings and supply it to your model. This is another way to deal. And always remember one thing, embedding layers will have two 2D. One is the samples, I mean how many words you have, and another is the sequence length. Means each entry or each word should be represented using 64 words. And you're having 1,000 overall, 1,000 words is what you're supplying. And each word should be represented using 64 numbers. Okay. Now, what will be the output of this? So this is fine. Input should be like this, right? Total number of words, and each word should be represented using certain numbers. That's given using this 64. Okay. When you have 1,000 words, when you do one hot encoding, each word is represented using how many words or how many numbers? If you have 10,000 words, unique words, if you apply one hot encoding on that, then each word will be represented using how many numbers? Anyone? I have 10,000 words. I'm applying a one hot encoding. Okay, or say you have 1000 words, I'm applying a one hot encoding. So how many numbers would be used to represent each word? To represent each word, okay, you'll have 1000 numbers. 0 0 0 0 0 0, somewhere it'll be 1 again, 0 0, all that. If you have 1000 words, you'll have 1000 words here, each of those. But when it comes to, say you have again same 1000 words which you are taking as input, and you're applying embedding. When you apply embedding, how many numbers should I use to represent a single word? Here you're saying use 64. You're saying use 64. Okay, and then initially what will be filled in this? In these 64, vector of weights in these 64 places, initially the weights will be random. Like your RNN model. Then how are these weights updated? Using your back propagation. Initially weights are randomly assigned, like your typical neural network. And then these weights are updated using go forward, calculate the error, come back and update the weights. Keep doing this. And then these will be updated for each and every word. Okay, then let us do this here, wherein we are saying that that's your embedding layer. You just defined it. Then I'm importing IMDb dataset, and we are importing something called as pre-processing, which will help automatically perform certain pre-processing tasks. There might be thousands and thousands of words which might be used in movie reviews, but we are interested only in 10,000 most commonly used words. Hmm? Just to ensure we run this algorithm faster, we are saying that first of all, consider 10,000 most commonly used words. First thing. Second thing is you cut off reviews after 20 words. In these reviews, take only the 10,000 most commonly used terms, and for each review, this is for overall all the reviews put together, the entire database put together, you're taking 10,000 most commonly used words, and for each and every review, you're cutting off the reviews after 20 words. Right? This is what we are doing. And you learn the word embeddings. Okay. So I'll erase this. Let me run this. And then I'm loading IMDb dataset. We are loading this IMDb dataset, and we are saying that number of words should be equivalent to 10,000. That's the 10,000 here. So take only 10,000 most commonly used words and put them into training and test data. In your training, you'll have inputs and output. In test, you'll have input and output. You run it. Then you pre-process the data. How do you pre-process the data? You turn the lists of integers into a 2D integer tensor of shape, samples, and the maximum length. So what do you mean by paired sequences? When I say paired sequence, what I mean is certain reviews might be only for 2 words. Here we are taking maximum length of review to be 20, right? Say there is a first review, review 1, or the first review, wherein you had 1, 2, 3, 4 in that way. Say you had 80 words, but then you are interested only in picking the top 20 words. After that, you cut off. This is fine. This is a perfect scenario. Say you have a second review, movie review, in which you have exactly 20 words. Wonderful if you get such a sequence. Okay, so you have here you have 80. So after 80 means after 20 you cut off. In the second review you have exactly 20. And in the third review, say you have only 10 words. If you have 10 words, then remaining 10 would be filled with zeros. Padding. Just to ensure that each and every review has equal size. Okay, so this is the use of that pre-processing module that we imported, and this is the use of the um, maximum length that we define, and you do padding. Wonderful, this is done. Next, what we do, here, this is just as an example. Okay, this is an example that I've given. That's it for word embedding. From here we started the code program. So you're loading sequential, flatten, and dense. So let me run those two, but then we need to run these also. Done. We are importing the data. It's taking a while because the data is getting loaded. Then you have sequential model, flatten, dense, all that. Then here you're saying that you want to first take the embedding layer as an input. Here we are taking number of samples, which is 10,000 most frequently used words. And you're saying maximum length should be 8. So what do you mean by that? You want each word to be represented using how many numbers? 8 numbers. Here, I just gave you example of each word being represented with 64. Here we are saying no, I mean that is just for explanation. Here is the right code. So we are saying each word should be represented using 8 different numbers. And you're telling input length will be maximum of 20. So that will be the length. So you'll have 20 words as a length. Once you get the data here, you then connect that to a flatten layer. So what happens usually is when you apply an embedding layer, the output that you get will be in 3-dimensional space. It will be 3D. What are those 3 dimensions? It will give you samples. Samples means your reviews. It will give you the sequence length. Sequence length should be 8. And then it will also input the numbers in that. Right? That's called as embedding dimensionality. This 3D should be flattened similar to what we have done in CNN, right? You flatten it and then you add that to the final dense layer. Why are we using sigmoid? Because using this IMDb dataset, we want to classify on whether a movie review is positive or negative. Should a movie review be positive or negative? We will understand. And then you have compile. You have your RMS prop, which is an optimizer. You're using binary cross entropy, and metric is accuracy. So define all of these, and then you fit a model. When we fit a model, all I'm saying is train, test. Okay, output and input. You first take the output and input of the training data and then test it on the test data. Here, what we are saying is when we want to test it, we are splitting this training data into 80% and 20%. So 20% of the data would be part of your validation data. So only 80% of this training data would be used for training. 20% of that would be used to validate your model. And then you want 10 epochs. Batch size should be 32. Okay. When I run this, you'll get some accuracy. Let's see what accuracy we get. Wow, this is pretty fast. Is it even going on to the GPU? I'm not sure. Let's see. Yeah, it's consuming GPU. There we go. So you have your accuracy. This is your training accuracy and validation accuracy. We are more interested in validation accuracy. We have taken only first 20 words in each review and still it worked well. 75% approximate is not a bad thing. But then if you just flatten your data, okay, if you just flatten this embedding sequences and if you train it on a single dense layer, then it treats each word in the input sequence. Each word that you supply to this model will be treated as a separate entity altogether when you do it in this way. The disadvantage is that in the relationship among the different words of the review is not considered. So what happens is, if you don't look at the relationship, someone might say, this movie is awesome. I slept for whole day. I slept for the duration of movie. It would treat this entire review maybe as a positive review, not as a negative review, because you're not considering all the words. This is sarcasm, right? Someone is being very sarcastic in saying that, yeah, movie is awesome, but I slept for the entire duration of movie. To capture such sarcasm and to look at the dependency of all these words, you can use pre-trained word embeddings. This is you're building your own model. Another way to handle this is use a pre-trained word embedding. Okay, don't generate your own word embeddings. Already people have worked on it, use it. And another reason on why people use pre-trained word embeddings is, uh, okay, so here let me, yeah, pre-trained. If you have less data and you cannot use your data alone, it doesn't work well. So at that point of time, you use this, and when you want to capture the relationship of multiple words in a sentence, that's called as co-occurrence, word co-occurrence. If you want to capture that, then you have to resort to pre-trained models. So here, what are we doing? We are jointly learning the embeddings along with the classification on whether that review is positive or negative. What are we going to do as part of this pre-trained or pre-computed models? You can learn embedding vectors from a pre-computed space, okay, and then supply it to your model separately. It is exactly the same kind of rationale that we have used for CNN models. Okay, when you have less amount of data, then it's really not meaningful to take that less amount of data and then start using it in embedding layers. Okay, and how are the word embeddings pre-computed? How is it pre-computed? It is pre-computed using something called as, so let me put it here, word embeddings are, it's word, sorry. Word embeddings are pre-computed using word reference statistics. The idea of having this kind of dense pre-computed network, it's in some sense an unsupervised learning task. Okay, you learn about what that unsupervised learning means, but then there are two widely used things. One is called as word to vec. Word to vec is an algorithm which will convert words to vectors, numerical vectors. And who came up with this word to vec? Google came up with this word to vec, long back. The guy's name was Thomas, Mikolov. In 2013, Google came up with that. It did an amazing job, right? Um, Here, there are various pre-computed databases that can be downloaded from Keras itself directly. And another famous technique which people use as a pre-computed embedding is GLOVE. GLOVE stands for Global Vectors for Word Representation. Global Vectors for Word Representation. This came to light from Stanford researchers. in 2013. This came in this came in 2014. This came in 2013. This is also based on coming up with word co-occurrence statistics. They have taken data from Wikipedia. They have taken data from a lot of good English, media channels, and then they came up with this. So we can use anything. We can use glove, or we can use, basically um, word to vec. You can use any of the techniques. Doesn't matter. So what I will do is we will download the raw data set first. We are going to uncompress that. I mean, we will download the data set which is not from Keras. We will directly download it. Okay, and then we are going to use it to perform the uh, embeddings, and then we will classify on whether our review is positive or negative. Okay, and we are going to make use of glove. Do you know what this glove has? 100 dimensional, so 400,000 words. So for all these 400,000 words, for each and every word, word one, whatever be that word, 100 numbers are used to represent each and every word. Word 2 also is represented using a 100 a vector which has 100 numbers. We will make use of this glove, and we are going to do our task in terms of building this embedding and running the model. It would take a while, but that's okay. We will have to train at the end of the day. We don't have any other choice. So it would take a lot of while, friends, and yeah, don't worry too much about this. This is a data set which we are going to supply you. We are going to supply you guys with the data set, but let me first check whether this location is still valid or not. Wonderful, it's there. And then we also, I've downloaded and kept it handy because it's lengthy thing. And then run it. Anyways, code would be shared with you all, don't worry. And once again, I repeat, you cannot overnight become a programmer. It's just going to make things complicated if I explain each and every line. Probably for the next 4 or 5 days, we'll be just doing that explanation part. Okay, so there are too many lines. I just skipped that. It's taking a while because the data sets are pretty large. That's okay. Let it take a while. And still the GPU didn't trigger off. CPU is 33% utilized. Memory is 8.3, so nothing to worry. So only 50% and 30% is being used. So that means there is no deadlock somewhere. Things are fine. We are just waiting for the processes to complete. Come on, complete. This is just the word embeddings, okay? This is just the word embedding that you are learning. After this, we have to build RNN model. Friends, don't assume this is RNN. Okay, if you're assuming in that will be difficult. So the raw data has 88,582 unique words. That's a raw data. Okay, and then the epoch started. It's taking roughly 2 seconds. That's pretty fast. 2 seconds, 4 seconds. It's very, very fast. And the model, if you observe, clearly is overfitting. Your training accuracy reached almost 100%, whereas your validation accuracy reached 55%. Okay, so it could be because of pre-trained models. Okay, and you're saying you don't train the initial layers. If you train that, it will take a lot of time, but maybe it will do the job for you. Here, what we do is basically whenever you run a model, you always save it. It's a good practice to save your model weights, because each time when you run your model, you will get different results. It is always better to keep saving those. And then here I'm taking within this history. If this history is replaced with ABCD, then ABCD dot history has something called as accuracy, validation accuracy, loss, validation loss. If you see here, accuracy, validation accuracy, loss, and then validation loss. So you run it and you understand on what's happening with respect to training loss and validation loss. Okay, you have training accuracy and validation accuracy also. It's pretty, it's decreasing, increasing, decreasing in that way. But then wherever you get the maximum accuracy and wherever your validation accuracy is also maximum, you stop there and consider that as final. You can also say that, do you know what? I don't want to use a pre-trained model like Glove. I want to just directly train my model. If you directly train your model in this way, wherein I'm just taking embeddings and training with this, it would not give you good accuracy. I can run and show it to you. Okay, roughly 52. There we got 55% accuracy. There is 3% difference in the accuracy. Purely subjective. I mean, you have to take a call on is it good or bad. But then if you again plot your accuracy and loss, look at that, training and validation accuracy. Immediately after the first epoch, your model started overfitting. But here, it at least took a while, right? So those kind of challenges, yeah, certainly you will run into. Okay. Now, let me get into RNN model and first explain RNN. Then we will combine embedding and RNN, and then we will run the RNN model. Okay. I mean, these advanced algorithms are not easy to explain. Neither is it very easy to understand. Okay. So the one way is to spend time again and again watching the video so that you get accustomed to this, right? All right. So RNN model has a recurrent connection. What do you mean by recurrent? If I say you have an RNN model, it will have an input and it will have an output. And then you'll have this recurrent connection. Input output recurrent connection. This recurrent connection is something which will keep saving the data in memory. This is called as loop and state. Okay, this is how it is. And then initial layer, as I've told you, initial hidden layer will be all zeros, null. Then you have input, which is sequence of inputs, sequence of inputs. And then you're saying output is a function of input and state. So here, the output that you get here would be input and the previous state. Again, the output which is going to come out would take this input and the previous state. And finally, you get an output. Whatever is the state here, that will be the output. That is what is given here. So the output that you get here or here, anywhere, what is it? You take the input here, you take the weights here, you multiply these two, and then you get this integration component. So it's a dot product of weight and input. So you'll have all the weights here, you'll have all the inputs, you multiply those two, you get the integration. And then pass it to your activation. Okay, that will give you one output. But then you're also getting an input from here. So you take the dot product of these weights into the previous state. And you'll also have bias. That will give you the output, which will go out. I repeat once again here. You're taking these weights and you have your input. You multiply these two, dot product. That's what is being taken. And you take that and supply it to your integration. Okay. But this integration component will also take the input from the previous state. So you have the previous state. This is state, previous state, all the values, multiply it with u. Then when you multiply with those two, you get some other value. You add this and you add this. And of course, every neuron will have a bias. Once you do that, you get this integration component. Take that integration component and supply it to the activation component. Whatever activation function you use. That would give you an output. That's going to be the output here. Okay. Using NumPy also we can implement the same, stuff, and then I can explain you even using NumPy, the same thing. And this code is how we use NumPy, and then using NumPy you'll understand the output, basically the output of the model. So when I say time steps equal to 100, then you're saying you want how many time steps in this way? This is 1, 2, 3. In this way you have 100 time steps. dimensionality of the input feature set of all these inputs is 32, and then output features have 64. Right? And then you apply this. I mean, I think we'll not have time to go through that. Then we will run a simple RNN, and then we will let our algorithm run, and then we will take a break. Okay, so please pay attention here. It is very simple. It is not as difficult as what you all are thinking. It is very, very simple. You just need to get the logic. From TensorFlow Keras, you are importing simple RNN. You are importing the sequential model. You are importing embeddings. You again need not import, but then that's okay. And then you are defining your sequential model. You're adding embedding layer, and you're saying that I want maximum of 10,000 words, and each word should be represented using 32 numbers. And you're adding a simple RNN, okay, and you're saying you want 32 time steps. Okay, you're saying you want 32 time steps. And if I run this kind of a model, you will simply have one RNN unit. That's it. Nothing else. Okay. But then how do I ensure that I keep everything in memory? Sometimes you might want to stack the data. Okay. You want to stack a lot of layers together. If you do not give anything like this, if you do not say return underscore sequences is true, what your model does is it's going to stop. For example, here it will stop. It will just output. So here what we are trying to do is we are going to stack. We are trying to stack all of these together. Okay. If I stack all of these together, it will have multiple RNNs. Okay. You're stacking them together. You can run this, but the number of parameters that your model will learn would still remain the same. So you have 322080. Here you have 3,20,000 and 2080 here. The same number of weights are here also learned. Why? As I've told you, the weights that your model will learn will remain the same. Yeah, for all of your RNNs, the weights that your model will learn remains the same. Hence, there is absolutely no additional weight that your model is expected to learn. Then I'm going to take now the same IMDb dataset. We are going to take 10,000 most frequently used words, and this time maximum length is 500. So do not, in each movie review, take 500 words of reviews. If there is any review which has only 10 words, then you do this padding wherein you add 490 zeros. You do that and look at the space. Yeah, it's loading the data. Once we load the data, we are going to now run a simple RNN. We are not going to stack anything, a simple RNN. I'm taking the embeddings. Okay. Because if your input is textual in format, If you supply directly to your RNN model, your RNN model will reject that. It will reject. However, if you convert this textual format to a vector format, numerical vector, then this numerical vector, if it is supplied to RNN, your RNN model will accept it. Otherwise, it won't accept. And that's the reason why we are making use of embedding to convert this text into vector. You're converting text into a vector format by doing this embedding. And then you're supplying the output of this embedding as an input to your RNN. And why are you connecting that to dense with 1? Because you need to read this IMDb dataset, which is nothing but movie review. And you need to classify that movie review as positive or negative. And since it's a 2-class problem, we are using the activation function, which is sigmoid. This is called as specifying your model. Once you specify your model, what are the steps you are already aware of, right? Once you specify or define your model, what do you do as part of next step? You're going to compile the model. Once you compile the model, you're going to fit the model. So you fit it, and it's making use of GPU. Since you're not using any pre-trained embeddings, your model is, continuing. It is learning right from scratch. You're not using any pre-trained embeddings like word to vec or glove. We are not using that. Okay, we are training the embedding layer also. It will take time. That's the reason why it will take time. I just want to check for one epoch and see how much time it takes. And then let's see. Okay, it's taking roughly 30 seconds. So let's take a break and let's continue. That's why I've kept for only 10 epochs. Usually we run 100 epochs, etc. Right? Here it's less number of epochs because it's taking a lot of time. So let's take a break and let us be back by, it's almost 40. So let's be back by 12:50. Okay, and then we'll take it further. Okay, so no, certificates is purely based on attendance, Surya Narayana. Okay, and yeah, it's based on attendance. Assignments is an additional value add. If that's optional, if you want to do, as I've told you, there'll be an exam. You clear that, multiple choice questions, and then it'll be done. Yep, Manasa, we will put that on the learning management system. And slides are also there on the learning management system, Manasa. Then dimension of embedding. Yeah, yeah, I've explained, I think, right? All right. Yep. I'm wonderful. Yeah, I think we can proceed further. Do you have any libraries similar to WordWare Glove for medical dictionaries? Yes, Jivan. Okay, we have. We are doing a project for uh, a hospital in Malaysia. It's called a smart hospital. And there we have done something. But then, what is this? Can AI replace coders? I don't know, Manogna. But then, even to automate the coders and automate that, we need someone who can write code. You write code to automate the code. But yes, auto AI and auto ML, rather, I would say auto ML, has automated a lot of things. We don't know, Srinivas. You need to experiment. It depends on the context, absolutely. I mean, I don't want to disclose those things, Jaban, because it's our unique selling proposition. Okay, and also I'm a chief data scientist on that particular startup. So they asked me not to disclose. So I would rather not disclose. It's against the contract that I've signed with them. Okay, so we cannot. I cannot. At least I'm bounded. Okay, by the ethics, so I cannot disclose. Okay, anyways, because that's not as straightforward as the other word embeddings, wherein you just go get it. You cannot. And they're also productizing, so I cannot disclose at this point of time. They spent, I think, 8 lakhs only to get training on that. 8 lakh rupees to get their team trained on those stuff. Yeah, so it's amazing field to work in, by the way. All right, back to this. So here, when you build, now look at what has happened. Earlier, your model was just overfitting. Here, it reduced that overfitting to a great extent. You have 99%, and here the accuracy has reached 83%. Good. Can you do any better? Oh yeah, sure, certainly you can. Because just by increasing the maximum length to 500, it it could increase the accuracy in this way. You probably add more representations. You do some kind of you know you apply regularization techniques, and then it will solve the problem. History has accuracy, validation accuracy loss, and validation loss. So you have your accuracy loss, validation loss, and validation accuracy. And this is the same code that we have understood all these days. Same thing. There is nothing different. Wow, it's much better. Probably after fifth epoch or so, your model started overfitting, so you might want to stop there. After fifth epoch, then you have a loss. Okay, so that's how you proceed further. Loss also can be compared after which epoch the loss is diverging. Here it's increasing, here it is decreasing. So maybe after fifth or maybe fourth epoch, you might want to stop and proceed further. Now, simple RNN is not the only thing which is available. We also have something called as long short-term memory, and you also have something called as GRU. So we will have to discuss those. Where did this go? Okay, let me open the RNN with RNN slides. And let us understand about, oops, I think I will have to resort to learning management system because I don't have it readily listed. So once you log into your learning management system under my courses, you will find AP State Skills Development Corporation and our thing, and then here we should have RNN. Should have LSTM also. Let's see. Just reduce it a bit. Okay. So we have this long short-term memory and GRUs. These are the two variants that we have within Keras. In real world, you use either LSTM or GRUs. We do not use RNNs. Okay, please bear that in mind. That is just for our explanation and understanding. When you have too many words which are available, then what happens is your RNN network will grow beyond a point. It will grow beyond a point. And if you have too many RNN units, too many multiplications, then it is very easy to get into vanishing gradient problem or exploding gradient problem. It is very, very common in RNN, vanishing and exploding gradient problems. To solve that, we have something called as LSTMs and GRUs. LSTM algorithm was developed in 1997, not now. We're back in 1997. And the research started when people experienced a vanishing gradient problem. Vanishing gradient problem, which is pretty common. Exploding gradient problem is not common because usually the weights get initialized. I mean, the weights which get initialized are very small. So this problem is pretty common. To solve this, research started in 1997 on LSTM. This is a small variant over RNN, yet the small variation is amazing. Okay, so even if you have a long sequence, that's absolutely fine. RNN works very well. Sorry, LSTM works really very well. When it comes to LSTM, there are a few gates that you need to learn. What are these gates and how do these gates work? Right, this is what we need to learn now. So when it comes to LSTM, the only thing that you need to be aware of is different gates. If you can understand the different gates of LSTM, then you'll understand everything else. But before I go to LSTM, I also have to tell you something else. And that something else is that, like we have bidirectional RNN, and like we have deep bidirectional RNN, we also have bidirectional LSTM and also deep bidirectional LSTM. We have bidirectional GRUs and also we have deep bidirectional GRUs, gated recurrent units which exist. Okay, and here let's understand. Within each cell, within each cell, you will have an input gate, output gate, forget gate. Alongside these, we have two more gates. One is called as remember gate, another is called as select gate. Select remember. Hey, what do you mean by remember? What is select? Are these something to do with input gate and output gate? Hold on. We will learn that. We will discuss. Okay. Now, first of all, think about this LSTM as a gate of a dam. If you have a dam, if you open the complete gate, 100% of the water will come out, right? With full pressure. If you completely close it, 0% of water comes and they store the water in dam for summer season. If you open the gate a little, 25%. If you open the gate up to half, 50%, more 75%, in that way. Okay. How much data you want to process through your network depends on how much gate you want to open or close. If you understand this logic, good enough. So here, if I have stop words such as this or you know them, right, can, all these kind of words are filler words or connectors or pronouns, etc. So these kind of terms will be completely restricted from passing through your gate. So you don't want to learn those kind of words. Your model itself does it automatically for you. It understands that these terms are probably irrelevant. So those are excluded. How does your model understand those are irrelevant? Because these are the kind of words which frequently occur. If they occur very frequently, that means it's irrelevant. Okay, now, so we have this very important gate called as forget gate and very important gate called as remember gate. Remember gate is also called as input gate. Okay, what should you remember? Output gate is called as selecting gate. Selecting gate is called as output gate. And then you have forgetting gate. Forgetting a number means you're going to push that number to 0. When I say forget something, then all you're saying is push that value to 0. When you push a specific value to 0, that means you're saying forget. Okay, very, very simple logic. So here, you have the gates, values basically. If you have a value 1, that means you're saying don't forget anything. So 1 into 32, entire thing you want. Here you want only 80% of this, which is 8. Here you have 50%. You don't want anything in that way. Okay. And another very important thing is you have to store things in memory, right? Remember that? Like your RNN, what were you doing in RNN? Whatever new word you get, this is the second word, but then this first word also in some sense is being given as an input. So you're remembering that. And when you have a third word, this first and second word also are coming along. So in some sense, they are being recorded in memory. They are remembered. Okay. So whatever portion you want to remember, always add it. Take your starting memory, whatever words, I mean, initially it will be nothing. Nothing will be there in this. Whatever your model learns, say you pass review 1, movie review 1 through your network. It will take all those movie reviews, it will learn different words and save them in memory. Then you have second review. What will it do then? It will process the second review. Whatever it learned, it will add to the memory which was stored as part of review 1. So then this ending memory will have information about review 1 and 2. And this process will continue on and on. So this is an LSTM unit, which is used to store the internal memory. So how does it work? Let's understand. So you have A, B, C, D. These are the neurons that you have. Okay. Now the input to these neurons is a single list. So the input would be new word as well as the previous word. I mean previous output. Like for example, you're taking this new word, supplying it to your RNN, right? Instead of RNN, I'm saying we'll be using something called as LSTM. Why did I write, I mean, draw a bigger one? Because it will have many operations inside. Unlike your RNN, where you just have in this way, wherein you have in this way, okay, LSTM will be slightly lengthy. Okay, and we are now going to understand on what is there in this. F stands for forget. R stands for R here, stands for remember. And S here stands for select. And we have 4 neurons from A until D. And how is the input obtained? By just taking the previous output and current input, you combine these two and do it. We'll first understand the forget gate. So the new input and the previous output, both of these are used by the neurons A, okay, and it will create list of values which will go to this gate, forget gate. Okay, so what does that mean? This A will now have list of values, list of weights. These weights go to this, and if its gate value is 1, it will either stay the same or else it will move towards 0. Okay, if it is 1, it will remember. If it is 0, you're saying forget. If it is anywhere in between 0 to 1, say zero point 0.4 or zero point 0.6 or zero point 0.8, then you're saying you remember portion of that. Okay, this is how your forget gate works. Okay, now the next thing is remember. So the new input comes in and the previous output also comes in. We send it, we combine these two and we supply it as an input to these two neurons, B and C. The C neurons are going to be used as gate values. Okay, they'll be used as gate values here. Okay, and every neuron will have an activation function also. Simple, remember that. And usually what do you use? Sigmoid. Why? Sigmoid ranges from 0 to 1 and we want our gate values to be 0 to 1. 0 means forget everything, 1 means allow everything to pass through. So you have R, remember, right? So the values that come out of C will serve as a gate values. If those gate values are 0, then completely ignore it. 1 means completely process it, or anywhere in between. Then the output of B are the values being gated. Ultimately, what do you want to remember? These gates are used to control how much of the previous output and the current input should be remembered. Okay, how much should be remembered? And this output from A will tell you how much amount of the previous state should be forgotten. Previously, you'll have state, right? I mean, whatever your model has learned using previous reviews would be there. How much of that you have to remember? So, for example, in the previous state, you stored a few words, but then the same kind of words are coming from input and forget also, like the, is, am. These kind of words continuously are coming. That means they are, if they are appearing too many times, then these might be irrelevant terms. So you'll forget those from the previous memory that you have, which is called a state. So the whatever you learned as part of the current input and previous output, you remember that. And then based on this input and previous output, you update the state. So you have the previous state, add it to the current state, and take those two and process forward further. When you add the previous state to the current state, you'll get a new state. That state is also updated here. Okay, you update this state, you save it, and whatever you get as a result of this one, also take it forward to the next level, wherein you have something called as select. So we select some of the newly computed state. You have a newly computed state here, newly computed state. Some amount of this newly computed state, which is going here, is selected. So we again take the previous input or the new input, previous output, also supply it to D, which also has sigmoid activation function because we want the values in the range of 0 to 1. 0 means forget, etc. So, and use the output of this D as the gate values, for this S. The input to this gate is a new state, newly computed state. But we just run it through some activation function, tan h or some activation function. This is the same as sigmoid activation function. Okay, it will actually just squash whatever input values come. It will ensure that the values are in the range of -1 to +1 if you have tan h. Okay, so those values get gated to S, and then you get the output. You take the previous output, current input, supply them to A, B, C, and D. A will actually give the gate values to this forget gate. Second, you have the remember gate. This whatever values go to C, they'll give an output which are nothing but gate values for R. Okay, and then from this R, whatever output you get, that will be the new memory, the new values. You add it to this previous state values. Forget is what values from the previous state you want to forget, what values you want to remember. Remember means for the current state, what you want to remember, what you don't want to remember. Then add those two, it will give you new state. Update that new state and take that new state forward. And here, what amount of the new state is actually needed for you for the output? To know that, you run it through, you run this new state through your select gate, and the values of this select gate are given by this D. The beauty is you can completely forget what is here. You can completely ignore the data coming in, new data, and then you can completely ignore or select the new data to be output. It is completely, I mean, you'll have complete control here. And all the weights of A, B, C, D are learned using same gradient descent like we have been discussing until now. Eventually what happens is your long short-term memory will learn all the weights that will allow you to forget, remember, select the right information at the right time in order to give you the right output. And even more important thing is LSTM does not run into vanishing or exploding gradient problems. Okay, wonderful. Okay, then one of the famous variants of your, I mean, I'll not get into the math bit of it. It's the same thing. Okay. So the difference between RNN and LSTM is that RNN doesn't have too much of rigmarole here. You just take an out when from the previous hidden layer, you get an out input to this, and from the current word also you get an input. Job done. You just process it. Nothing much. You'll have neurons, which will have integration and activation. But here, when it comes to LSTM, you will have a few other things as well. Okay. Now, GRU, is it, I mean, you can do deep recurrent neural network. Similar to that, we have deep, long, short-term memory, and I'll not get into the depth of this. Okay. I think for GRUs, you have a separate explanation. Tomorrow, I'll briefly touch upon this, but just to tell you, it will be very, very simple. GRUs. It won't be uh, complicated at all because it's very simple. The only difference between GRU and LSTM is that when it comes to GRU, the forget and input gates are combined. Yeah, they are combined and it forms a single gate. So that means it will need less effort and it will be slightly faster than LSTM. And the results that GRU produces will be very, very similar to LSTM. So when you start working on RNNs, it is worth to spend time on LSTMs and GRUs. It is worth spending effort. Okay, so this is all about dealing with data. But then while we are going to discuss about these, I also want to tell you that these are a few latest of the things that you might want to understand. If you just want to navigate to that courses, you have AI and deep learning. You have to go to AI and deep learning course. Okay, this training would be very, very different. Okay, very different in the sense, until here, anyways, we discussed. Of course, we get into a little more depth. Okay, and this thing is very important when it comes to dealing with your text data. But transformer Excel, ExcelNet, these are the new things which are coming up. Auto AI or auto ML is another big, big field. By the time your students are if they are joining now BTech in AI, then by the time you complete 1 year, things will change. Drastically, they will change. No doubt about that. And also, there is something called as explainable AI. This is also one thing which is heavily being used, really heavily being used. Okay, so research people who are into PhD, etc., are professors, lecturers. The field that you have to focus upon if you want to really take it to the next level would be auto AI and explainable AI. Right? World is moving towards generalized artificial intelligence. Okay, and one more thing is, let me write it here itself. People, instead of using words, because in English you have a vocabulary size of 172,000 words. If you look at characters or alphabets, you'll have 26 lowercase characters A to Z, and you'll have 26 uppercase A to Z once again, and you'll have 10 digits 0 until 9. Then you'll have 22 punctuation marks. You'll have 4 accented vowels, and you'll have a space bar. All these put together, if you just add them up, it should turn out to be 89, if I'm not mistaken. So instead of 172,000, you can condense that to 89 and then start working on this. This is also something which people do. There is even condensed version of this which is going to have 49 characters. That means you convert lowercase, uppercase to lowercase. Then this will become 26. Suddenly you reduce it by 26. So you'll get another 63. Out of these 63, there are a lot of common symbols which are available. So you get rid of those also. You remove the accented vowels. When you do all that, wow, super cool. You'll have only 49 characters to deal with, not 172,000. This is also another thing that people usually work upon. All right. Having said that, I think we covered a lot of ground. I'm going to update the mind map. Please watch the mind map and take it further. Okay, so we are going to update it right away. I will ensure that the mind map is updated and you'll get access to the updated mind map in the next 15 minutes. All right, friends, thank you so much. Please give your attendance and yep, video, please watch it. Please replicate the code. We'll also upload the code because you all are requesting for that. And that's it. I think we should be good. All right, friends, thank you.